Hey everybody, here we are, lecture 28, getting down to the wire, second to last official lecture of the course. Again, this is going to be a short lecture. I'll do the reading quiz as usual. It's going to be a short lecture because I'm going to spend more time talking about this applet. This applet, Walter Fendt Huygens, which is at this URL, and I'll give that to you, is a much better way to talk about this mathematical material than going through the dry mathematics. This is an important lecture because, in addition to being second to the last, it sets up how lenses work. We've learned how mirrors work. We've learned how you focus and form an image with a mirror. You take an object, put it in front of a mirror. That ray goes here through the focal point. This ray goes here. This ray goes through the focal point and comes out here. That makes an image that's here. That's because of reflection from this mirrored surface. We want to do the same thing now with the lens, but to do that, we need to know how light bends at the interface between the vacuum and a material such as glass, which has a higher index of refraction. Here's the name of the game in today's lecture, and in lenses also. For a mirror, the reflection angle equals the incident angle. Here, there's a bending of the angle, and we need to know how big that is. Okay, so with that as a kind of a quick introduction, what's the answers here? Spreading of light into a spectrum is called dispersion. It makes a phenomenon in nature called rainbows, but that's because of dispersion. Okay. Index of refraction. The definition of the index of refraction is the speed of light divided by the v of the material. That's a kind of an interesting way to define something. We normally normalize. This is the thing we're interested in: the velocity of the material in glass, say, or in diamond or in quartz. Normally, we might normalize that by taking that velocity and dividing by the speed in a vacuum, which is the ultimate speed in all of nature. Here we do that inversely. It's a reciprocal. Okay, so what do we know about this? Okay, here we know for any material that you can't go faster than the speed of light. Okay, so v material is always less than the speed of light. V in a vacuum, in a perfect vacuum, is exactly equal to c, but we can't go faster than c. So if v is always less than c, n has to be greater than or equal to 1. Okay, index of refraction can be 1 for a vacuum, but it has to be bigger than 1. And here are typical numbers for the index of refraction for various materials. Here's vacuum. Air at STP is a little bit bigger than vacuum, but water is 1.33, glass is 1.5, and so on. Okay, so there's that. Okay. To understand how lenses work, you need to know Huygens principle. You don't need to know the principle of least action. If this were in class, we'd spend a little time about that. Okay, but here's what you need to know about Huygens principle. And it's kind of intuitive if you think about dropping pebbles in a pond of water. Okay, suppose I'm sitting in a little pond of water at the beach, in a little tidal pool, and I go plop and I drop a little pebble in the water. And you know what happens? I get expanding wave that expands outward from that point. It's supposed to be circles that are going around that point. So I get a little ripple. Okay. If I take that little single pebble dropping into water in a pond, that's the origin of Huygens principle. Because here's what Huygens principle says. Huygens principle says every point on a wavefront is a source of tiny little wavelets, little point wavelets that spread out at the direction of the wave. Okay, so if I were to drop not a pebble in this pond of water, but if I were to take that pond of water and take a ruler, take a meter stick, and instead of dropping the pebble, drop that meter stick in there, then I would get a wave that goes out this way, and this way, and later times here. So I get a plane wave that goes this way and this way. But Huygens principle says that this is really just a combination of all of those things, okay? So here's a wave coming against a barrier in a ripple tank, in a water tank, a plane wave. If that barrier wasn't there, the wave, here's one wavelength, huh? This goes like this and comes back up again. This is the wave front, and that's the intensity of the wave. That wave going this way, if this barrier wasn't here, I would get continuous waves that come across here, okay? But the barrier stops the wave there, okay? Out here, the wave doesn't know the barrier is there and it keeps on going. But at this point here, you get a little disturbance, okay? You get a little perturbation there, and that comes from taking this wave front here and adding it to all of those, okay? You'll see that more when we run this applet here, Walter Fent. This is not a course in material science. It should be. So we just give you a bunch of data from material science. Index of refraction is greater than 1. Diamond has the highest index of refraction of all. It's 2.42. Salt has 1.5. That's close to glass. Water is 1.33. Huh? You know this experiment. I take a glass of water, okay? If you haven't done this, do this. Take a glass of water, fill it into here, and stick a pencil in it, okay? If I were really a good professor, I would do this demo for you, okay? And you see the apparent bend in the pencil when you look at that. Maybe I'll do a video of that in the next one just to see that, okay? That bending is because of this bigger index of refraction in the water than in the air above it. So what does the index of refraction tell you about a material? For any wave, starting from physics 111, way back in sound, velocity is frequency times the wavelength. Where does that come from? That comes from lambda equals velocity over frequency. Frequency is 1 over the period, so that's v times the period of the oscillation. Sorry about that there. That says distance equals velocity times time. Huh? So that's kinematics from the 6th grade for you. Distance equals velocity times time. For a wave, it says that the wave travels 1 wavelength at velocity v in the time, the period of the oscillation. Okay. So now with this new definition of velocity in terms of the index of refraction, that goes like lambda is v over f, lambda is c over n times that. Okay. So here's the punchline. The punchline is the larger the index of refraction, the smaller the velocity, the shorter the wavelength. Okay. Here, for example, is air and glass. This has an index of refraction which is less than that, okay, and it has a shorter wavelength here in smaller wavelength in the higher index of refraction. Okay. This is the geometry for Snell's law. The geometry for Snell's law is just similar triangles, and it says if I want to know how much the bend of the ray is for a given index of refraction pair, this triangle is similar to that triangle. That says this goes like that in terms of index of refraction. I get Snell's law here, okay? And homework problems in the back of the book will get you comfortable doing that. But what I really want you to understand from a physical point of view is what's going on in terms of the bending. And here's the story, okay? Here's an interface between 2 materials, okay? And the way I've drawn it, this one has N1 less than N2. For example, this would be air and this would be water down here. Index for air is like 1.0003. Water is like 1.33. Okay. Here is the perpendicular to that interface. Here's my glass of water, my pencil sticking in the water. The pencil doesn't bend, but it looks like the pencil bends. And it bends in the following way. It bends according to Snell's law. And if you plug the answers in to the numbers, you get that bending smaller here. But here's what you always think about. Here's the punchline for MCATs, if you're taking the MCATs and you see the story. That ray always bends toward the material toward the normal in the material that has the greater index of refraction. Okay, and that works both ways. Okay, so if this is the ray of light coming in here, I shine a flashlight here, and the ray goes this way and bends this way. Okay, so it bends towards the normal, to the perpendicular. Here's the normal. Here's the normal in the material that has the higher index of refraction. If you want to turn that around the other way, if you want a ray going from the dense material to the less dense material, well, you just change your thinking. It bends away from the normal in the less dense material. Those are two different ways of saying the same thing. Okay. Dispersion of a prism. I like to do that in lab as a demo. It's pretty. It's beautiful. It's kind of boring. I'm not going to talk about internal reflection. This is the end of the course. You're tired. We're all tired. You've got projects to work on. This is how fiber optics cables work, and it's important for technology. It's nice physics. I'm not going to talk about it. That's already up to 10 minutes. I want to spend more time talking about the Huygens principles, so catch you in the next video on Huygens principles demos. Thanks, bye.